You might not hear me that well anyway because my voice is barely hanging on today. So if I panic, give me a second to get a cough drop. Um, so I'll be talking today about some groundwater modeling work we're doing with a lot of really leadership from from UABC, the Autonomous University of Baja California in Mexicali. And I'll be talking about some of the scenario modeling work that we're doing for specifically Reach 4 of the Colorado River Delta. And my co-authors on this are Karen Schlatter, who you all heard talk now from Sonoran Institute, and also Francisco Zamora from Sonoran Institute. Eliana and Jorge are both from UABC, and Chad McKenna is from Geosystems, and Jeff Milliken works for the Bureau of Reclamation Lower Colorado Regional Office. And before I move on, I'll be talking a lot specifically about Reach 4. So if you look in the background of this picture, this shows the active restoration in Reach 4 that Sonoran Institute has been doing for the last 6 or so years. This restoration site is primarily cottonwood willow, and right now it's about 300 acres, but there are plans to expand the network in this local area up over 1,000 acres. So we have some significant investments in this area already, which will tie into the rest of the talk. Okay, so you all have seen several presentations that included work on the Colorado River Delta, but I'm going to provide a little bit more background information on how the river changes in Mexico as you go from Morelos Dam, there goes the first time, Morelos Dam up here at the international border, the northern international border. The Colorado River serves as the border between Arizona and Mexico on Reach 1 and Reach 2. And then Reach 4, down where we're doing a lot of active restoration, is down here. And then finally, the Gulf of California. Primarily for the riparian corridor, we're looking at Reaches 1 through 5. And then once you get into Reach 7, this is more estuarine conditions where there's interaction of high tides from the sea. A quick walk or flight down the river, as it were, from Morelos Dam, which is up here off the screen. This is Reach 1 from the air. And what you can see in Reach 1 is there is a lot of water in the river. And in addition to a lot of native cottonwoods and willows that are still supported by shallow groundwater, and occasional accidental flows that come through Morelos Dam into the Limotroph region where the river is the border. And you can see obviously a lot of water in the channel as well. There's also a lot of tamarins throughout the corridors, of course there is on all of Colorado. Going into Reach 2, the river starts to disappear underneath the sediment. This is a picture from just before the 2014 pulse flow with Eloise from the Nature Conservancy. And you can see in this area there's a lot of salt cedar that is pretty dense. It looks pretty healthy. So there's still relatively shallow groundwater here, but it's starting to fade down from the subsurface. I feel like I'm going in and out here. Okay, as you go down to Reach 3, by this point, this is the Colorado River in Mexico. There's not much river left at this point. There is still a decent amount of salt cedar, but the groundwater is so deep that it doesn't even support dense salt cedar in this reach. This also happens to be really close to the town of San Luis, Rio Colorado, which is named after the river that no longer flows through the area. By the time we get back to Reach 4, I'll talk about this more as we go, but there's enough shallow groundwater influence from the agricultural areas that groundwater becomes, I should also say that this is not during the pulse flow, this is just like background conditions. There's shallow enough groundwater that you have areas of surface water, and then from the picture on the first slide, the restoration side is just off the left side of the screen. And you can see cottonwood and willows along the riparian corridor, and also in some of the historic waters in the area. And there's significant enough water in Reach 4 that we do have year-round water and support things like beavers. So there's evidence. Yes, there is water in some parts of the delta. So in Reach 4 specifically, I'll be talking about that quite a bit. Well, for riparian areas in general, they rely on either surface water or shallow, low salinity groundwater to support the vegetation as well as the other habitat conditions that we want. And specifically, it's important for supporting existing habitat, but also helping us identify areas where we could do some active restoration and have long-term success. Shallow groundwater areas are targeted for active restoration, like Peter mentioned before. Reach 1, where there's a lot of influence from accidental influence from accidental flows from the dam, and then reach 4, which is where I'll be talking about the groundwater modeling effort. So in reach 4, it's a complicated plumbing system, even for groundwater, and it's influenced by a lot of factors, again, that are not in our control, like agricultural return flows, groundwater pumping, evapotranspiration in the corridor, precipitation, so the water that comes in from the Colorado River in the U.S., and then, of course, some active work to get environmental flows. So I want to key in on reach 4 and kind of show you a conceptual model of what we're looking at for water in this reach. I'll point out again, so reach 4 is this lighter blue area, and all of these polygons are active restoration sites. These 3 sites, this is the site that was shown on the first slide, and these are 2 other areas that were in various stages of developing, and then this is the Chausey site that Peter mentioned. So the point of this is there's a lot of active restoration planned for reach 4, and let's walk through the water budget components. So under an ideal scenario, we do have river inflow into reach 4. So there's some water coming in, there's some water. Next, there's some influence of subsurface agricultural return flows. So when you irrigate, of course, there's irrigation inefficiency, and some of the water that you put down goes through the soil profile, becomes groundwater, and that groundwater can go back into the riparian corridor or away from it, depending on the gradient of groundwater. Evaporation, transpiration is just water lost from the system, and this could be, of course, both from plants and evaporation from open water in the system, as well as evaporation from bare soils. So environmental flows and rainfall I've kind of lumped into this slide. All of these water drops indicate points where we have the potential to deliver environmental flows to reach 4. So, for example, there's a turnout from the irrigation canal that will provide water for this restoration site, and different irrigation turnouts that provide water to the restoration sites, as well as potential deliveries to the river channel and the backwaters. I kind of lumped rainfall in here, and rainfall is very, very minimal. Of course, down here we're looking at less than 2 inches of rain per year on average, so it's a really small percentage of the overall budget. So I have a couple slides that just show how some of these different factors could influence groundwater levels in reach 4. And this just shows curves of smooth groundwater depth data along a transect right by the restoration site. On the y-axis is depth to groundwater, so as you go down, the groundwater is deeper, and just day of year across the bottom. And what you see is something that might look something like a natural hydrograph, where you have higher groundwater in the spring that could be something like snowmelt runoff, and then lower groundwater levels later in the summer. But if you look closer, what this really is an effect of regional irrigation. Okay, so the irrigation season starts in December and peaks in March, April, and then goes away. And there's very little irrigation after mid-April. So after the agricultural inputs decrease, you see a big decline in groundwater levels, and it's probably a combination of evapotranspiration and decreased agricultural inputs. And this chart shows the same background data in the curves, and then these are observed points from the 2014 and 2015 during the pulse flow and phase flow influence. So in this chart, what you can really see is the jump from these curves up to some shallower groundwater, and that's due to the environmental flows. So that's just one example of how you can have, in some cases, influences of over a meter of increase in groundwater levels due to the environmental flows. Sorry, barely hanging on here. So the importance of groundwater is not lost on us on the restoration areas. So there are really 2 big components of what we're doing right now. The first is groundwater monitoring through a network of groundwater piezometers. Some piezometers have been out in the site since 2005, but there have also been new piezometers installed through minute 319 and additional funds that we're using to install piezometers. And the key things for us are groundwater elevation, groundwater depth, and groundwater salinity, which is another big issue that I'm not going to touch on too much today. And the idea is we want to know how irrigation and environmental flows are changing groundwater levels and potentially use the data to adaptively manage the sites. And what I mean by that is if we see that groundwater salinity levels start to increase, we know that we need to put more fresh water down in the system. If we see that groundwater levels are declining, we need to put more irrigation in to support the root systems of the trees. So the second major component is a project that's funded through the Desert Landscape Conservation Cooperative to do some groundwater modeling for Reach 4. And the idea, and this is what I'll be spending the rest of the talk talking about, is to determine what the depth to groundwater distribution would look like across Reach 4 given combinations of different scenarios. And really, it's what are the reasonable expectations for what we'll see in the future with groundwater levels, and what does that mean for active restoration as well as conserving existing vegetation that's out there, which is what I have here. So we can use it to select our sites, prioritize sites that are suitable for restoration, determine our long-term water needs and environmental flow needs, and really use this as a baseline for discussions on how much water do we need to support these areas. So be talking most of the rest about the groundwater modeling stuff. So the first is to refine existing depth to groundwater thresholds that are available in the literature, specifically targeted for the delta. And what I mean by that is there's lots of research by Light and Stromberg and others that provides general depth to groundwater thresholds for cotton willow, for example, up to something like 5 meters. We think it might be a little bit shallower in the delta, so we want to look at that. And the way that we're doing that is really twofold. We can look at, well, really we can, okay, so I want to back up here and say that we have remote sensing data available through minute 319. And what that is a combination of LiDAR data to get us both canopy height, ground elevation, and what Jeff Milliken also did is combine that with a spectral image analysis to look at what the current vegetation composition is throughout the Colorado River Delta. So we have super high resolution, awesome data on vegetation conditions for the pulse flow. And what I'm in the middle of doing right now is looking at the relationship between that vegetation and depth of groundwater to see what we think the levels of groundwater, cottonwood willow, and other habitat types need in the Delta. And then I mentioned some objectives on the previous slide, but the outcome of the modeling effort is really to determine the areas that will be suitable for different habitat types based on the groundwater modeling outputs. Okay, I'm not a groundwater modeler, so I'm going to present some stuff and talk about it generally, but without going into too much detail. We are really building on an existing regional groundwater model that was developed by UABC, Eliana and Jorge. And they have a mod flow model for the entire Mexicali Valley. And you can see it here. So this is the agricultural area, obviously, of the Mexicali Valley. The Colorado River goes through here. And then up on this side, this is the Brawley El Centro area. And the international border is here. So this figure shows the modeling mesh throughout the region. And if you look closely, you can see that they already had a somewhat finer scale model for Reach 4 of the riparian corridor. And they've actually updated this model to give us a transient groundwater model for Reach 4. And I trimmed various points from other presentations. So on the left is just some of the key information that went into the model, including hydraulic conductivity of the subsurface. This map just shows all of the pumping wells in the Mexicali Valley. As has been alluded to, there's a lot of groundwater pumping for agriculture and other purposes in the area, but we have some level of information on the outputs, the yield of groundwater pumping in the valley. The other thing that we have, and this highlights a couple different things, but this shows all of the irrigation districts in the Mexicali Valley. So similar to irrigation districts in the U.S., these are these districts will get allocations of water, and they allocate them to the different farms on site. And there's some information available from the water that each modulo is the district in Mexicali, how much water they're getting. And just the other thing I'll point out here is you can see that we're in Reach 4, we're bordered by about 3 different irrigation districts of importance. Okay, I'm going to dive in a little bit to the modeling components conceptually without getting too much into the weeds here. Across the top are the input categories, amounts, and the drivers. And what I want to drive home on this slide is that there are an infinite number of combinations of things we could look at. So we had to lump different drivers to see what they could potentially, what effects they could potentially have on groundwater. So for all of these scenarios, there's essentially a baseline, an increased or reduced. So with agricultural return flows, we can either look at, or we're going to look at current agricultural return flows. What would happen if they applied more water and still had the same amount of percolation and recharge? And then what would happen if they, if less water was percolated? And really, this is what it comes down to, the drivers. So what could cause less agricultural return flows are the things we typically think of as positive, increasing efficiency. Canal lining, fallowing of fields, if they use less water-intensive crops, all of those things will actually reduce the groundwater recharge that supports the riparian area. Something. So riparian corridor ET could either increase or decrease. It could increase if we take out all the salt cedar and replant it with native vegetation that uses more water, as an extreme example. But for this, we are looking at 3 different levels current. What would happen if we converted 10% of the salt cedar and arrowweed to cottonwood willows? There would be a net increase in evapotranspiration. And then finally, what might happen if there was a 15% reduction in salt cedar ET? This is the number I have, is something like what might happen if the salt cedar beetle arrives to the delta. Environmental flow deliveries, none, which is our baseline. High and low, which is to be determined based on reasonable values that we're coming up with people that are working on environmental flows. We're setting our boundary conditions as the upstream end of Reach 4, so we have to have some way to account for what's happening in Reaches 1 through 3. So to simplify all those and lump them, we can say, okay, upstream groundwater is either going to stay the same, it's going to decrease, or it's going to grow up. And we're using historic groundwater level data that we have for that. And you can see that we lump a lot of these drivers, and this is why. Just with all those combinations, we end up with 81 scenarios. And really what we want to get out of that is monthly groundwater elevations, especially monthly groundwater elevations during the growing season. So we end up with almost 1,000 groundwater surfaces that we need to get. So it's a lot of work, a lot of GIS work on the back end. Then we can combine the LiDAR topography data, depth to groundwater elevation to get depth to groundwater, and then summarize the depth to groundwater conditions and habitat support. Really quickly, I want to walk through an example looking at some historic data. What I'm going to show is actually the process we're using for active restoration design, but it's a similar process to what we're going to do with the model results. So I wanted to present an example since I don't have final results yet. This is the interpolated depth of groundwater surface throughout Reach 4, with blue and green being shallower groundwater, red is deep groundwater. So what we will do is take this information and overlay it with habitat potential categories. And this is what I'm using right now for active restoration. So if you have shallower water, you can have dense, high-quality riparian habitat. And by the time you get deeper groundwater, which right now I have is greater than 3.5 meters, then you're looking at more mesquite upland for a sustainable habitat type. You overlay those, and you get nice, pretty maps. LiDAR data is amazing. This shows an example of the overall restoration plan for one of the restoration sites, just using that background information. And this is where we're going. And the idea is that we'll do this for all of Reach 4 and roll it up and say, okay, this is how many acres could potentially support this vegetation type with this set of groundwater conditions. So, last slide, Daniel, I promise. Recently completed, we've compiled all the existing data we have, including lots of data that's coming to us real time from minute 319. But we're still working on certain things like ET estimates, environmental flow scenario development, which is a complicated process. And I've started looking at the depth of groundwater thresholds based on my remote sensing data. And it's challenging, more challenging than I anticipated, so we're still working on refining those results. And with that, I want to thank the Desert Landscape Conservation Cooperative, who's funding this project, with matching funding from the Lincoln Institute. And if I can recover my voice for 5 seconds, maybe I have a chance for questions.
One question, and let me make sure I get the microphone to you. One question. Going once. Going twice. All right.
You might have already answered this when you were talking about the different characteristics of the reaches, but is there very much like salt water in the groundwater?
That's a good point. I didn't touch on it. There is roughly a gradient of lower salinity water near the Morelos Dam to higher salinity groundwater as you get farther and farther down. So we don't have a lot of good information from Reach 5 right now. But Reach 4 is borderline to saline for riparian vegetation as it is. So we're getting pretty close to limits. And groundwater salinity is something that we've started to monitor. I mentioned this on the site too, but it's definitely a challenge. And as you get even farther downstream on the extreme in the estuary, the salinity of the groundwater and the surface water is many times what the salinity of seawater is.
All right. Well, thank you very much, Matt.